Alright class, today we're going to determine the relationship between the strength of an acid and that of its conjugate base. We'll be able to calculate Kb from a knowledge of Ka and vice versa. We'll be able to explain how acid strength relates to the polarity and strength of the HX bond, where X is the anion and H is the proton in your acid. And we'll be able to predict the relative acid strengths of oxyacids. We're also going to get into neutralization reactions a little bit in the dilution equation and how that relates to some of the upcoming lab procedures. This pairs well with the quest on acid-base chemistry number 3. Alright, last time we talked about Kw. We know that our H plus concentration times our OH minus concentration gives us our Kw, which is 1.0 times 10 to the negative 14th. That's due to the autoionization of water. So if we multiply those things together, it stands to reason that Ka is, times Kb is also equal to Kw. Anytime you have a transformation where there's two reactions happening at the same time, and the sum of those reactions give you your overall reactions, you have to multiply our K values. So for a certain weak acid, says our Ka is 2.0 times 10 to the negative 5th. What is Kb for its conjugate base? Well, since they're related, we know Kb has to be equal to Kw divided by Ka. And we can just plug them in. 1.0 times 10 to the negative 14th divided by 2.0 times 10 to the negative 5th. Let's see, 1 to the negative 14 divided by 2.0 e negative 5. Oh, e negative 10th, I went the wrong direction, sorry. 5.0 times 10 to the negative 10th. Alright, so my Kb is 5 times 10 to the negative 10th. Alright, so acid-base behavior and chemical structure. Looking at the strength of binary acids. So I actually have some notes in here. I'm going to just open up on the side to help explain the graphic and the chart. When we're looking at binary acids with anions from the same group, the bond strength will decrease with size, which then increases the acidity. So part of that has to do with the distance, the inner nuclear distance. If you're looking at the distance between the nucleus and the valence electrons, when we get to periodicity in the next unit, we'll be able to apply that a little bit more. We also know that binary acids with anions from the same period, the same row, acidity increases with increasing electronegativity. If we think about that, electronegativity is our desire to want to attract electrons to ourselves. If we are more electronegative, we're going to hold on to our valence electrons more tightly. It's going to be a more polar bond that way. Since it's a more polar bond, it is easier for that H plus to dissociate, and it makes that H plus stronger in that sense. And if we can dissociate more, we're more likely to be strong in that regard. You can see the things in group 4A have very little acid or base character. Group 5A, we start getting into the weak base territory. We know ammonia is a classic weak base. Anytime you see NH3, just think that's a base. Don't even question it. Water, we already know auto-ionizes. It can be amphoteric, so it can be an acid or a base. But hydrogen sulfide is a weak acid. So it dissociates a little bit, but it's not as electronegative as its neighbor, hydrochloric acid. We know that chlorine is way more electronegative than sulfur. Therefore, it's got a more polar bond, and therefore it's going to ionize more completely. Now, oxyacids themselves. When I say oxyacids, I'm talking about things with polyatomic ions in them. So we're looking at polyatomic ions. Okay, so in oxyacids in which an OH is bonded to another atom, the more electronegative Y is, the more acidic the acid. So here, if we're looking at our chlorate, or actually HClO, that is hypochlorous acid, that is still relatively weak, but it is more electronegative of these weak acids that we're looking at here. These are all weak acids, but they are all things with polyatomics in them. So chlorine has a greater electronegativity than iodine, so you can see that even though their structure is basically basically the same, the electron density is shift more to this region over here, more to the chlorine, leaving this H more readily available to protonate or ionize in that regard. Whereas iodine, even though it's a larger atom, it's not as electronegative, so there's still a shift in electronegativity, but it's not as great in comparison to chlorine. Okay. So electronegativity matters when we're looking at the oxyacids. The other thing that matters is the number of oxygens. So for a series of oxyacids, acidity increases with the number of oxygens, which makes sense. We know oxygen's electronegative if we've got like we can do like little arrows for comparison. Say we've got a shift in electronegativity this way. It would help if my pen was working well. Say we've got a shift in electronegativity this way. All right, if we add another oxygen in the equation, that arrow gets a little bit larger. Here we've got 3. That arrow gets even larger. And then when we have 4, we've got all of our electrons being shifted over. Makes it very, very hard to maintain this bond here. This is really the bond in question, is the OH bond, because that's when we're going to ionize. When we ionize, we're going to be left with our oxyanion. So if we think about it, it makes sense because oxygen is more electronegative, we have more electron density. Electrons are being pulled away from hydrogen, and when we pull those electrons away from hydrogen, it makes it more positive, and by making it more positive, it's more likely to ionize. And this is just within a series. We have the same polyatomic family, I suppose. We have the chloric or the chlorate ion, and then perchlorate is over here, and then we've got chlorite and hypochlorite. If you go back to acid and base naming, the naming for all of those things are literally based on how many oxygens are in the system. Some other common ones we like to look at, we've got nitric acid. We know nitric is strong, but nitrous, one less oxygen, is weak. So this is strong and this is weak. We also can look at sulfuric acid. We know sulfuric acid is strong, but H2SO3, sulfurous acid, is weak. So just keep those things in mind. If you see less oxygens than normal, it's probably going to be weak. Okay. We also have something called resonance. It's been a while since we talked about resonance. Resonance in a molecule is based on the Lewis structure. When we have Lewis resonance structures, we are able to take the double bond in our structure and move it around. You can still draw the structure in multiple valid ways. It's just that the double bond reasonably could be in either place. And what we end up getting is a hybrid molecule. Whenever we have resonance, it means that the electrons in the double bond are actually delocalized, meaning that they're basically, there's not really a double bond there at all. It's really that the electrons are partially shared between both groups of atoms. So what I end up getting is that if you think about what the normal bond length is, and I'm going to draw this skewed, we know that double bonds are shorter than single bonds. If I have delocalized electrons like this, or not delocalized, if I have two structures like this, but they're actually just the same, the combinations of the two, my true structure is a hybrid of those, where the bond lengths are somewhere in between. And you might remember seeing the dashes. Those are delocalized because the electrons in the double bond are shared equally between both atoms that are attached to the carbon. So anyway, long story short, what this means is that when we have resonance in our conjugate base, it stabilizes our carboxylic acid group. This is a carboxylic acid group. Normally there's an H attached on here too, and when there's an H attached on here, that's when it has more acidic character. But when we have resonance, it stabilizes the base. It makes the conjugate acid more acidic. So carboxylic acids are actually pretty strong for that reason, because they're stabilized by resonance, meaning that we have extra electrons floating around that are equally shared. So we don't necessarily need the electrons that we're sharing with our hydrogen, so therefore the proton becomes more acidic. And we become more acidic, obviously, because if hydrogen's electron deficient, it's more positive, it's more likely to ionize. Okay. So we also have the neutralization reactions. For acids and bases, we know that if we mix a strong acid and a strong base, or really any acid and any base, we get neutralization reaction, where the hydrogen ions and the hydroxide ions form water molecules. So my example, I've got a strong acid, so it's a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. They mix together, and they end up forming sodium chloride and water. Notice the states. This is aqueous, meaning that when it's aqueous, we can get it back out of our solution. So if we were to heat our solution and evaporate the water, the ions in solution from the sodium and the chlorine would form a solid, and we'd actually get salt out of it. So we call this a salt. Obviously it's table salt, but just in general, any salt, if you recall, is a metal ion and a non-metal ion resulting from a neutralization reaction. So it's kind of a double replacement reaction in a sense, right? We've got our metal ion from our base, we've got our non-metal ion from our acid, and it comes together and it forms our salt. This one literally here is salt, but it can be anything. You could have HCl and what's another base? I could have magnesium hydroxide, and that would give me magnesium chloride. This is still a salt. Again, it's just any kind of acid and base where they're mixing and neutralizing themselves. We get a salt. Now, the idea behind this is what led us to develop the lab procedure called a titration. So a titration is a controlled addition and the measurement of the amount of a solution of known concentration. So if we take something that we know the value of and we react it with something unknown, we can then determine the concentration of our unknown. So what we have is we have a burette. A burette looks like a giant test tube, and it's got graduated cylinder markings on it, but actually goes in reverse order. So 0 is at the top, actually 50 is at the bottom for doing 50 milliliter burettes. And as we turn the little knob, the knob is called a stopcock. As we turn the knob, we allow our acid or base solution to drip into our container, which has the opposite, either an acid or a base solution. So I'm usually always mixing an acid with a base or a base with an acid. We're able to add it dropwise. It allows us to be really precise with how much volume we're adding, and we can figure out our concentrations from there. How might we do this, you ask? Well, we have to think about it. we're actually diluting a solution by adding more liquid to it. So we're going to basically have an application of our dilution equation. So if we slowly add our base to the acid until both are neutralized, we're able to see what the concentration of our acid is. The reason this is because of something called the equivalence point. This is the end point of our titration. This is where H plus and OH minus are equal. If we know what our OH concentration is, and at the end point or the equivalence point we know that it's equal to H plus, then we can go back and calculate our moles of H plus and therefore calculate our molarity to get our concentration. If we're using an indicator, the equivalence point is where it will change color. So like I said, dilution equation, here we go. We know that M1V1 equals M2V2. And we know that M, that's talking molarity, not moles. If we think about this, we know that molarity, big M, is equal to moles per liter. If we multiply that times a volume in liters, our liters are going to cancel. So by multiplying each of our volumes times our molarities, we end up figuring out that our moles of acid are equal to our moles of base. Okay, so essentially this is an applied version of the dilution equation. MAVA equals MBVB. Okay, so here's an example, and this is very similar to something you'll see in the quest. A titration requires 50 milliliters of 0.1 molar NaOH solution to reach an M point with 10 milliliters of acetic acid solution. Determine the concentration of our acetic acid solution. Okay, well, I have my molarity and my volume of my base. I'm going to leave things in milliliters because we'll end up working in millimoles and things will still cancel. You don't always have to convert, but as long as it's consistent. If you have one that's in milliliters and one that's in liters, then you should definitely convert. All right, so I want to know my concentration of my acid. That's what I'm looking for. I know I have 10 milliliters of my acid, and I know I've got 0.1 molar NaOH and 50 milliliters. Okay, so if I multiply 50 times 0.1 and then I divide by 10, I can get my concentration. So 50 times 0.1 divided by 10, my concentration is going to be 0.5. All right, 0.5 molar. Not too bad. All right, and it makes sense if we have a very dilute solution of NaOH and we used quite a bit of volume. 50 milliliters is pretty substantial, and that only titrated 10 milliliters of our acid. It makes sense that our acid is going to be a lot stronger. Or not stronger, but more concentrated. That's another thing we have to remember, is the difference between strong and weak acids versus concentrated and dilute. Concentrated means it has a high molarity, dilute means it has a low molarity. Strong means it will dissociate completely, weak means it does not dissociate completely. All right, so now for you to try one. 19.3 milliliters of an unknown acid solution was titrated with 31.2 milliliters of a 0.0125 sodium hydroxide solution. Find the concentration of the acid. Okay, so you should have gotten that your molarity is 0.202 molar if we're going to 3 sig figs. We have our acid volume, we have our base volume, and our base concentration. Multiply the 2 on the right, then divide by 19.3. Okay, ooh, a little too far. So one of the things we have to keep track of, that's just finding the concentration itself, but we also have other situations where they may tell you both your volume and your concentration, and we want to know what the resulting molarity will be. So dilution does play an effect. We are adding things that are dissolved in water to other things that are dissolved in water. So overall, we are diluting our concentrations as we add. So it's important to make sure we're paying attention to those things, because in these kinds of reactions, we will end up having a limiting reactant, and our concentration will be impacted by that dilution. So if I have a 600 milliliter solution of hydrochloric acid, 4.4 molar, and I add that to barium hydroxide, I know I'm going to end up getting my resulting salt, barium chloride, and water. I am going to have to balance this, so as I go through and balance, I'm going to check my waters first. Looks like I've got 3 hydrogens on the left side and 2 on the right, but I know I need to double my chlorine here, and that probably will lead me to doubling my water. Does that make sense? 2 times our oxygens. Yep, there's 2 oxygens, 4 hydrogens, 1 barium. Okay, so we're balanced. Okay, so I have my original concentrations here, but what I need to really do is figure out how many moles I have. This is a limiting reactant problem. I need to figure out what molarity of barium chloride I have, therefore I need to figure out how many moles of barium chloride I have. So I know that on one side I've got 4.4 molar times 0.6 liters, and I can figure out my concentration there, 4.4. My calculator turns on, 4.4 times 0.6. I've got 2.64 moles of hydrochloric acid, mole, and then I also know I have 4.6 molar times 0.338 liters. All right, 6 times 0.338, and I get 1.5548. Okay, 1.5548 moles. Okay. Well, we need to do mole-to-mole ratios for each of these to figure out how much barium chloride we actually have. So if I have 2.64 moles of HCl, I have to use my mole ratio. I know I have 1 mole of barium chloride for every 2 moles of HCl, based on my balance equation. So half of that, what's half of 2.64? 1.32? 1.32 moles of barium chloride would be formed, right? Let me double check. 2.64 divided by 2, yes, 1.32. All right, and 1.5548 moles of barium hydroxide leads to my barium chloride. So 1 mole of barium chloride and 1 mole of barium hydroxide. Well, it's easy to see which one's the limiting reactant here. Our hydrochloric acids are limiting reactant. We make less stuff with our hydrochloric acid, so this is how many moles of barium chloride we end up. Now, remember, this is just moles. We're looking for molarity. So, to figure out our molarity of barium chloride, we need to divide by our volume. The question is, which volume do we divide by? Well, we've diluted our whole solution. This is a total volume. So we've got 0.6 liters plus 0.338 liters. That's our total volume that we have to divide by here, because we've diluted our whole solution. So this is the number of moles in a new total volume. Okay, so 0.6 plus 0.338 is going to get us pretty close to 1. 0.938 liters. So we can do 1.32 divided by 0.938 liters, and we get 1.41 as our molarity. 1.41 molar for our barium chloride. So that's how concentrated our salt will be after this is neutralized. It's pretty cool. So you'll see a couple of problems like that on the quest. Realize that they are limiting reactant problems, and you'll have to do a couple extra steps. Okay, that is all for today.